In this video, we're going to be looking at how to perform a one-sample proportion hypothesis test. This is going to be a hypothesis test that one population has a proportion that's equal to some specified value. So the first thing that we're going to do here in any hypothesis test is we're going to state our significance level alpha. Alpha, as a reminder, is the probability of making a type 1 error, and we can, as the researcher, decide what to set our alpha level. Usually we're going to use 0.01, 0.05, or 0.10. And again, that alpha level that we choose is going to depend on how important it is for us not to make a type 1 error. So if making a type 1 error would be really bad, then we would set alpha to be 0.01 to be small, keeping in mind that alpha and beta are inversely proportional. So if we if we decrease the probability of making a type 1 error, we would increase the probability of making a type 2 error. Moving on, our next step is to state the null and alternative hypotheses. So in a test for one proportion, the null would be that P, the population proportion, or the proportion, the percentage of our population that has our characteristic of interest, is equal to some value P sub 0. And then we would need to choose between one of the three alternatives. So one possible alternative is that P is not equal to P sub 0. That would be two-tailed. A second possible alternative would be that P was greater than P sub 0, which is right-tailed. And then the last possible alternative is that P is less than P sub 0, which would be a left-tailed test. Okay, moving on, then we are going to third calculate the test statistic. And the test statistic for a one population proportion test is a z-test statistic. We need to find P prime, where P prime is the sample proportion. And we can find that by taking x over n, where x is our number of successes and n is our sample size. P sub 0 is the value we're testing in the null hypothesis, and then Q sub 0 we find by taking 1 minus P sub 0. Okay. Step 4, the next thing that we're going to do is we're going to determine the p-value of our test. And so I've got the definition listed here for a p-value. We're told that the p-value is the probability that we observe a value of our test statistic, that's this guy up here, that's as extreme or more extreme than the value we actually observe, assuming that the null hypothesis is true. And so the way that we calculate the p-value is going to change depending on what type of alternative we've selected. And so I'm going to have three cases here, so I have to squeeze in pretty small. So one case, I'm drawing a standard normal distribution because we know our test statistic is a z distribution. And one case would be that we have a right-tailed test. And in a right-tailed test, the p-value is going to be the area under the curve that lies to the right of whatever your test statistic was. Okay, so here's z. If you find that z value, whatever this area to the right is going to be your p-value. And we already know how to find areas under the standard normal curve using the normal CDF option. Another option is going to be if you have a left-tailed test. And so if you have a left-tailed test, then the p-value is going to be the area to the left of your test statistic. And then the final case is going to be if you have a two-tailed alternative. And if you have a two-tailed alternative, you are still going to calculate your test statistic, z. And that test statistic might be positive, it might be negative, but wherever it is, you're going to find the p-value by taking the area that is more extreme than your test statistic. But you need that area in both tails because we're testing a two-tailed alternative. And so those z values, whatever one you end up with, if you get a positive z-score, you're going to also take the same z-score but negative. If you get a negative z-score for your test statistic, you're going to take that same one but also positive. And those areas are going to be symmetric since the curve is symmetric about 0. And so basically the p-value is going to be the sum of these two areas, which could also just be 2 times one of the areas. So the p-value would be the sum of the shaded area. Okay. The fifth step is we are going to compare our p-value that we just found to the significance level alpha from step 1. And then we have to make a decision. And in step 6, we have the decision criterion, which says if our p-value is less than or equal to the alpha value, we're going to reject the null hypothesis and conclude the alternative. If our p-value is greater than or equal to alpha, we are not going to reject the null hypothesis. And finally, our conclusion is going to take the form of either the data provides or does not provide sufficient evidence to conclude the alternative hypothesis. Back here in step 6, if we do not reject the null, the data does not provide evidence to conclude the alternative. If we do reject the null, the data does provide evidence to conclude the alternative. So the not here in step 6 would go with the not language in the interpretation in step 7. So we're going to go ahead and look at an example. Okay. In this example, it says in a given year, 91.4% of all U.S. families had incomes above the poverty level. And during that same year, it says that of 400 randomly selected families, sorry about that, whose householder had at least a bachelor's degree, 391 had incomes above the poverty level. And we are told at the 1% significance level to determine if the data provides sufficient evidence to conclude that the percentage of families that earned incomes above the poverty level was higher among those whose householders had at least a bachelor's degree than among all U.S. families. So I know there's always a lot of language to get through. We're going to start here with step 1, which is stating the significance level. And you'll notice in this problem, they give it to you. Most of the problems we're going to face, they do. And so alpha is 0.01. 1% is 0.01. The next step, step 2, if you look at the steps we just did, is to state our null and our alternative hypotheses. So our null hypothesis is going to be that the percentage of families that have a bachelor's degree is going to be the same as the percentage of all U.S. families. So P equals 0.914. The alternative, we're looking for language that's going to specifically help. is it says, do the data provide sufficient evidence to conclude that the percentage of families that earned incomes above the poverty level was higher among those whose householders had at least a bachelor's degree? So what we want to see is if the percentage of those who are above the poverty level is higher than the rest of the U.S. population. Okay, so there's our hypotheses. Step 3, we are going to calculate our test statistic. So remember that test statistic is Z equals P prime minus P sub 0 all over the square root of P sub 0 times 1 minus P sub 0 over N. So we're going to need to find P prime. P prime is, again, our sample proportion, and that's just going to be our number of successes out of the sample size. So this says during this same year where we had the data, about 91.4%, it says they sampled 400 randomly selected families whose householder had at least a bachelor's degree. That's our sample size. And of those, 391 of them had incomes above the poverty level. So that gives us 0.9775 as our P prime value. So now we're just going to plug in. Oops. And when you do that, you will get 4.53 as your Z test statistic. Step 4, as a reminder, is to calculate the p-value. This is a right-tailed test, and that's because we chose the greater than alternative. And that tells us that the p-value is going to be the area to the right of 4.53. And this isn't very to scale because that should be way out here. That's going to be a tiny p-value. So you can find that by doing normal CDF in your calculator. We want the area starting at 4.53, going up to some really large number. And we're looking at a standard normal distribution. So the mean is 0, standard deviation is 1. And you get a p-value there of 0.0000295. So what we're saying is that if our population proportion is really 0.914, we would only see a sample proportion of 0.9775, 0.000295% of the time. Extremely unusual for us to observe this sample proportion if in fact the population proportion is really 0.914. So step 5, and I'm going to combine that with step 6, is where we make our decision. So if our p-value was less than or equal to alpha, that's where we're going to reject the null. Clearly here 0.0000295 is definitely less than 0.01, and that leads us to reject our null hypothesis. And so our last step is to interpret what we just found. And we're always going to start by stating the significance level. So at the 1% significance level, we did reject, so that means the data provides sufficient evidence to conclude the proportion of households who have at least one person who holds a bachelor's degree that are above the poverty level is greater than 0.914.